First of all, I would like to thank the organizer for giving me and my family the opportunity to be here in this lovely location, enjoying not only the nature but also exciting science. So I'm going to give 2 lectures. Today I will take you through a very fast surfing through the area of iron-based superconductivity. And tomorrow I will focus more on different experimental techniques which help us to address various aspects of competing electronic orders found in these materials. So this is a short summary of the 2 lectures. So today I will just introduce the basic concepts to iron-based superconductors, some of their phase diagrams and the different competing phases there. And I'll focus on the key electronic ingredients which we think they are responsible for their physics. Obviously, we still do not understand this family. That's why all these ingredients are necessary when we want to develop theoretical models. And then I will try to find, at the end of my talk, if there is time, I'll focus in particular on iron chalcogenide family, which has exciting variety of phenomena, including the observation of high TC superconductivity in a monolayer of iron selenium on strontium titanate. Tomorrow I will focus more on experimental techniques, and I felt that some of the relevant ones, in particular in iron-based superconductors, are how we determine nematic susceptibilities, which is a probe of nematic electronic order. Then I'll talk about angular resolved photoemission spectroscopy, and it as a powerful tool to distinguish the orbital effects. And then I'll present some of the quantum oscillations in high magnetic fields, also under high pressure, that we've been working recently. So let's recap a bit the phase diagram that also peers showed last week. This is the timeline of superconductivity. It started more than 100 years ago, and since then the temperatures kept on going higher and higher. Obviously, the most remarkable discovery was the high TC superconductivity in '86. Then in 2006, we have a new family with lots of materials of the iron-based superconductor that I'm going to talk about. And since then, the remarkable almost room temperature superconductivity found in hydrogen sulfide and lanthanum hydride last year towards 250 gives us the hope that one day we will find a room temperature superconductor that we will be able to apply in everyday life. So I think that's the hope we need to have, and to carry on looking for them and never giving up. So, I mean, every discovery in high temperature superconductivity was by chance. Unfortunately, we have the BCS theory, which was able to explain conventional superconductivity, but after it was discovered. But anything else afterwards, it wasn't a well-designed formula. And often people look for different things. And that's also the story of iron-based superconductors. So this is Hideo Sono from Tokyo University. So he's a material scientist, and he was looking to find transparent semiconductors to use them in computer screens and other display devices. So that was his aim in his research. That's why he applied for grants for. And by doing this search and looking through the periodic table very systematically, he started replacing different elements, and he came across this lanthanum oxide, copper, and chalcogenide family. And then he thought, well, what if I want to make a magnetic? Let me replace copper with iron, and then maybe in that way I can use also the magnetism. And doing the search, he found that lanthanum iron phosphorus oxide superconducts at 4 Kelvin. Obviously, these days, if somebody finds a 4 Kelvin superconductor, there's not too much excitement, I'm afraid. You know, it's ignored in literature. You hardly manage to publish it, and not too much has happened at that point. However, later on, after he replaced phosphorus with arsenite and also doped the system, a 26 Kelvin superconductor was discovered. And that was the point where everybody started being interested, because now we have a material above the conventional superconductor which it's a new family, it has iron in it, so it's an exciting prospect for understanding and for finding new materials. So I thought when I was looking at iron age of superconductivity, just to look back in time, what happens in iron age. So this was more than 2,000 years ago or close by. I realized that Britain became an island further away, and now we're becoming an island again. But here is, in Iron Age, we developed tools made out of iron, much stronger than copper or tin, and this helped really led to significant advancement in human development. Obviously, they could make tools, they could make lots of weapons, they could conquer, and so. But now, let's think, what will Iron Age of superconductivity would do? I hope it won't be 2,000 years before we reach room temperature superconductivity, but we hope this family of new superconductors will help us to develop those tools, both experimental and theoretical, to understand very complex correlated metal, both to understand even the bigger brother family, the copper oxides, but also to develop all the tools we need such that we can calculate and hopefully predict from now on high temperature superconductivity. So let me take you back. Now this is as I mentioned, the first material was lanthanum iron phosphorus oxide. Is made out of layers. So one layer is iron phosphorus, and iron has an oxidation rate of 2+, and lanthanum oxide is the separating layer. And it just had a small TC, and doped with fluoride, TC increases slightly. So this is the trigger compound. So this is now the arsenite. Arsenite is isoelectron rigorous phosphorus, and in this case, the parent compound without fluoride is a bad metal with a structural transition. So it's an antiferromagnetic metal, which I'll talk in a minute. But only when we dope the system with fluoride, so we replace an oxygen with fluoride, then we donate electrons to the system. In this case, the magnetism is suppressed, and a superconductivity of about 26 Kelvin is established. If you go further and play around with chemistry, look in the periodic table, replace lanthanide with samarium, then this is one of the largest TC found in this family of about 55 Kelvin. So this is how this field started, and since then there's been lots and lots of families of these iron-based superconductors. And this is pictures of various crystallographic structures for different family of compounds. The first one, which is structure will be the simplest, is iron selenium, which is 1,1 type compound. All this telephone number labeling here in reality comes from the number of atoms. So we have iron selenium 1,1, we have lithium iron arsenide 1,1,1, we have iron strontium iron arsenide, iron 2 arsenide 2, 1,2,2. So often people start just referring to this labels without telling the name of the compound anymore, but this is where it's coming from. So what's common in all these materials, at least in the ones I show you here, is that the conducting layer, the layer from which superconductivity emerges, is form of this iron bonded to either selenium atoms here or arsenide atom here, and all form this conducting plane. The TC varies between families. As I said, in the initial family, which is 1111 compounds, it reaches to about 56. Then it plateaus around 38, 40. And iron selenium in a monolayer form is believed to go much higher. And I believe one of the more reliable reports is about 75 Kelvin. So if we look in the periodic table, another issue of terminology, often you might hear about pnictides and chalcogenides, and this is because if you use a bonding element to the ions, which belongs to the nitrogen group, so if I have phosphorus, arsenite, then they are called pnictides. But if you use a bonding ion from the chalcogen family, the sulfur or selenium or tellurium, they are called ion chalcogenides. And we have a lot of degree of doping, so if you replace cobalt with iron, you donate an electron. If you replace nickel with iron, you donate 2 electrons. Sometimes also ruthenium and rhodium are used for doping effects. So these are all part of 3D transition metal ions, where often we have very rich physics coming from the fact that we might have strong correlation as well, and we have Hundsru's coupling and other effects playing a role. So now let's discuss a few phase diagrams of these materials. So this is one of the most steady family of compounds, which is the 1, 2, 2. Here we have barium, iron, cobalt, arsenite, so we add electrons to the system. As I mentioned before, many of these materials start as being antiferromagnetic metals. This is the resistance versus temperature. It has a kink to about 140 Kelvin, and it's a bad metal. As you add more cobalt, eventually the resistivity becomes even linear, and then becomes more square in temperature, evolving towards Fermi liquid-like behavior. So the phase diagram has this transition, and the further study, as I show you next, discovered the first transition is actually a structural transition. Then it has a magnetic transition, and once we suppress the magnetic order, we develop a dome of superconductivity with maximum TC close to about here, about 6%.
Sorry, your resistivity curves are not the best one. We don't even see superconductivity. You don't have zero.
So all these curves, are shifted. This is the resistance versus the normalized values at 300 Kelvin.
But in superconducting state, you have zero.
These curves are shifted. So this is 0, but they are shifted vertically. So sorry, this is the superconducting transition. However, this curves is not absolute units. They are relative units in relation to room temperature to be able to plot them on the same graph. Yes?
What's going on in this green region? So it looks like it's an overlap between AFM and SC. So is it superconducting, or is it?
So this is still superconducting. The question is if this is still some sort of a mixed state, and I'll show you in another composition where they found other phases forming in that regime. Yeah. Well, it's a transition. So the question is what type of transition is. When we start in this phase diagram, we have a transition here, and that's the point of transition. However, as you introduce doping, you notice that these two curves actually disperse. So in reality, if you do a derivative of these curves, they are 2 features, and you need other probes to identify that. And here is another probe to identify the transition at high temperature, and these are structural measurements. The parameter which is plotted here is the degree of anisotropy, so it's how much the in-plane A minus B lattice parameters change against each other. And this starts at this TS transition, and then this is the second transition, which is identified by neutron diffraction. But what's interesting here is that this anisotropy, which is an in-plane anisotropy, which later I will refer as nematic transition, seems to be affected once the system enters the superconductivity. This is telling us that whatever order is set up by this transition is competing with superconductivity. And here are graphs showing now the magnetic response of the system from neutron diffraction on a similar composition of the same family. This is now the neutron diffraction signal integrating intensity versus temperature. And in this graph, it's really clear that we have these 2 disentangled transitions. One set up by the structural effects, and the second one where the magnetism kicks in and it has an order parameter. Again, as we reach the superconductivity, also the magnetic signal is affected by by the development of superconductivity. That means they do compete for the same electrons. One anomaly referring to this material is the magnetic moment detected here. It's extremely small. And this came as a bit of a surprise, because if you think of a iron 2+ in the right crystallographic environment, it should have a very large moment, whereas here, magnetic moment is below 1 magneton Bohr. And I'll mention in a minute more about that. So this is a summary more about what's the finding related to this 1 to 2 family of compounds, where you have this generic phase diagram that you might find in other family of superconductors. In this case, there is a structured transition followed up by a magnetic transition. And the magnetism that develops here is a counted antiferromagnetic order. So let's describe a bit this picture. So we have, will be the in-plane ion plane. Arsenic are sitting above and below this plane. Because of the Gliese symmetry, we have 2 inequivalent ion sites, and this is the unicell in a 2 ion per unicell. Then, as we go through this transition, the system distorts, and it distorts along the ion-ion bonds, and it becomes orthorhombic. And afterwards, in this orthorhombic structure, there are some localized spins which order in a collinear fashion. So we have ferromagnetic chains ordered antiferromagnetically. So that's a general picture that is found in this family of compounds, but in others, which was the kind of physics we had to deal with, thinking that these systems are now pretty itinerant. So we are dealing with bad metals. In other family of compounds, things can deviate a bit from this picture, and this is just the 1111 family. Often, at least in this case, there is a very sudden drop, so it's like a first order transition separated this magnetic phase from superconductivity. If you add cerium, which in itself has its own magnetism and can affect behavior, again, the behavior of structure transition is slightly different from that of the magnetic moment. So they kind of separate from each other. Now another contrast is the family of the hole dope. So far, cobalt doping gives electrons, and in the hole dope case of the same 1 to 2 family, we replace potassium for barium atoms, and we hold up the system. And here, there is no differentiation between the structural and magnetic transition. And as I mentioned earlier, concerning your questions, deep inside the superconducting phase, new phases have been discovered where the system seems to recover back its tetragonal C4 symmetry once inside the nematic state, inside the superconducting state. So that's telling us that there is a strong competition between what type of magnet is stabilized and how that competes with the changes in structure and potential different type of magnetic orientation, especially of the spins from being in plane to potentially switching towards the c-axis. Now, these materials have extreme tunability, and that makes them also very beautiful to study because we can use different tuning parameters. So far, I talk about doping, but here, with pressure, it can have a similar effect. You suppress magnetism and reach the region of superconductivity. This reminds us of the tunability of organic superconductors. Again, with both the applied pressure and chemical pressure, we have antiferromagnetic phase neighboring superconducting phase, and even more exotic phases, including spin liquid phases that Lucille was mentioned today, was found in this family. Another way to tune this magnetic phase and get to the region of high TC is through isoelectronic substitution. Now, So when we use, in this case, we replace phosphorus for arsenite. Phosphorus is a smaller ion, but it has the same number of electrons. That means we do not dope. We just apply a chemical pressure effect. And a beautiful thing about this way of tuning is that we do not disturb the ion plane. So when we dope in the ion plane, we also induce a lot of disorder. But isoelectronic substitution is one of the cleanest way to explore the phase diagram of the superconductors. And in our research, we found that we can follow quantum oscillations over a large range of composition because of this cleaner way of tunability. Yes?
So what happens if you're not doping with phosphor, something that's not isoelectronic? So earlier you showed you replaced barium with potassium, which is whole doping. But what if you whole dope it on different sites? Does it look the same?
So, okay, so you're asking how universal all this doping is. There is universality in certain aspects, and I think especially this phase diagram compared with, well, let's say this phase diagram have very similar trend in behavior. Nickel and cobalt can be rescaled to really follow each other if you account for the same number of electrons being donated to the ion level. So I think if you can scale back how much you dope and how much your Fermi surface changes, you can scale the systems. However, if you also change anything structurally, then you won't be able to do that.
On the phosphorus substituted phase diagram,
Yes?
there's this grey line in between the blue and the green regions. No, the grey line.
Okay, this one.
So is there any explanation for
So this is, in reality, similar to what I showed before. This is a structural transition, a nematic transition, before the system enters the magnetic phase.
Okay, so
It's just rougher points at the beginning when people show their phase diagram is not as refined, but in reality it's the same physics as I show in a 1 to 2 panel.
So would that behave as a spin density wave, or is it non-Fermi liquid?
So the non-Fermi liquid occurs over here. So I will have some graphs later showing actually there is a linear T resistivity found here, suggesting that there is a quantum critical point underneath this dome. Question is, where is it coming from? Is it determined by the magnetic phase, or is it determined by this nematic electronic phase? This is similar to the isoelectronic substitution, but this time you put ruthenium, so it's a 4D ion. And when you put ruthenium, it has wider bands compared with ions, and it makes, also suppresses correlation faster. And this has been probed by Ironbased, showing much wider bands. Okay, and now if we summarize what we think about iron-based superconductors, it's worth going back to cuprates, to one of their phase diagrams, just to emphasize the main differences. And those differences come from both correlations and the details of their electronic structure. So parent compound in cuprates is an antiferromagnetic insulator, a MOT insulator. We need very strong correlation to understand its behavior. In this case, we have bad metals. We can still use band structure to give us the general pictures of what these materials will look like. So here we have very small carrier density in the system, and we also have lots of bands. And all this, the orbitals, orbital degrees of freedom are also important, and we have all the 5 orbitals are relevant. On top of that, the systems have very high density of states, despite the fact that they have small carrier density, which makes them prone to this type of instabilities, electronic instabilities. In cuprates, again, there's a single band. The superconducting gap is well established, and everybody agrees on. In this case, because of the complexity of the electronic structure and the role played by orbitals and correlations, the things are not yet established in terms of what is the universal gap to describe all these materials. And in terms of now general pictures, which are the main competing phases that one can think of, especially applicable to this 1 to 2 families, which is the most studied, so that's why I would like to focus on things which people agree on, has this component. So as I said, the structure transition is believed to be of electronic origin, and the fact that it breaks a rotational symmetry and we have anisotropy in plane is called a nematic transition. If we use the electronic doping, it's believed that there are even stronger fluctuations above this transition, which are potentially responsible also for superconductivity in the system. This is the order parameter that I showed you earlier from the experiments associated with this anisotropy, the nematic order parameter, and how it follows the magnetic magnetization of the system. On the hole dope side, it seems like the nematic and the magnetic order parameters are much closely correlated. So what we need to understand in these materials to really work out their superconductivity is what is the origin of the pairing mechanism, and also how we can, in a simple model, if that's even possible, to account for a variety of physics shown in this family, but also in much larger spectrum, which deviates from this picture. So, okay. So let's now focus on the details of the crystallographic structure. So as I mentioned before, what's common to many of this iron-based superconductor is the iron layer, which is bonded to either a pictogen or chalcogen, and it's common to all the family of compounds. Now, if we look more into detail, what happens to iron inside of this layer? Iron sits inside of a tetrahedron made up, in this case, of arsenite atoms in the corner. And if we place this iron 2+, which has 6 electrons in this environment, this crystal field effects in this environment will lead to the splitting of the EG and T2G levels. And now if we lower the symmetry further, and we have the trigonal symmetry, what we found that the relevant orbitals, which are likely to play the most important role for the magnetism and electronic behavior are the DXY, DXZ and DYZ, which are degenerate in tetragonal symmetry. One can break this degeneracy either through orbital overdrive effects of these orbitals, or obviously through another lowering of symmetry in orthorhombic symmetry. And often the question is, what is the trigger? Is it electronic, or is it to do with the lattice itself suffering the distortion? And this is still an open question, but I want to present today the picture coming from an electronic point of view. Now, what empirical law found by analyzing lots of materials and looking to this perfect tetrahedron, it was found that, especially in the 1111 family of compounds, it seemed that transition temperature is maximized when this tetrahedron is regular. And since then, it's been found quite universal that TC, it's achieved when this tetrahedron is regular. So this is telling us that the Hoping integrals and all the other effects which determine the physics and the high TC should come from understanding the local environment of iron inside of their little tetrahedron. And since then, as in other family of compounds, there's been deviation from this point of view. This is, I just want to add as a side, but I'm not going to discuss. So we have the instead of having the square environment, now this ion plane can have further distortion, which can give to new type of family of compounds with much complex symmetries. Okay, so now I want to focus on the itinerant picture to understand this material. So in particular, I will talk about Fermi surfaces. So as I mentioned before, some of these materials are better metals than others. So this is lanthanum iron phosphorus oxide. This is the first one discovered. It has a TC of about 4 Kelvin, and it's a reasonably good metal. So in principle, we should be able to understand it quite easily. This is band structure calculations performed using V2K software, which we are also able to use by inputting lattice parameters. And what is it telling us? This is the spaghetti, lots of bands there, but what's important is what happens at the Fermi level. So here we have hole-like bands at the gamma point, which are this type of entities. And at the Z point, there is a center, another hole band, whereas at the M point, these are electron bands, and they look like this quasi-two-dimensional Fermi surfaces. And this type of bands also are dominated by different type of orbital characters. So both the hole and electrons have XZ or YZ character, whereas the Fermi surface, which is more two-dimensional, it has a DZ square character. And now if we put everything in the Brillouin zone, this is how a Fermi surface will look like. It's form of this concentric electron-like at the corner of the Brillouin zone and hole band-like in the center of the Brillouin zone. And as I mentioned earlier, in this material, these are semi-metals with relatively small carrier densities of about 10 to the 20 centimeter per centimeter cube. Now, to confirm this picture of a good metal, obviously we need some experiments, and this is one of the first experiments we did on quantum oscillation in this compound. These are Tor measurements, where one glues a tiny little crystal of about 50 microns at the end of AFM cantilever, and the bending of the lever is related to the torque, which is magnetization times B magnetic field. What you see here is that for different orientation, the response is different. So this is torque for a paramagnetic system should have a B square dependence, and on top of it, you have the quantum oscillations. Now, if you rotate, this is close to B parallel with the AB plane. You see the features coming from superconductivity, and there are no more oscillations in this orientation. And in quantum oscillations, you subtract this background. Then you look at the oscillatory signal on its own, and you Fourier transform, and these oscillations are directly related to cross-section areas on the Fermi surface. And when you put all this information together, here are different frequencies similar to what I just showed you as a function of the angle between the normal to the plane and magnetic field. Then you notice this dispersion. So they are all kind of quasi-two-dimensional dispersions for the different bands. And this is where we need band structure calculations to help us work out what they might mean. So when you have a single band system, it's very easy to work out the shape of your Fermi surface. But when you have multi-band systems, there is a difficulty because especially if you look at these two cylinders, they are pretty similar. And there are certain details which differentiate them, which is the degree of warping, for example. And when you check their band structure, you notice that the red curves disperse more compared with the blue curves. And then when we look at the experiments, we know that these red dots are more dispersive, so they are likely to come from this larger band. Now, yes. So this is B1 and B2 are the neck and the belly of this particular. And these are, we see the best electron bands here because they have lighter masses. So this is something else which is important. In the quantum oscillations, the lighter masses are easily to see compared with heavier masses, because also the probability of scattering when they describe the cyclotron orbits. Now, when we So this is the spectrum. So obviously you also look at their intensity. So if you are worried about combinations, about other effects, which often, in torque, this is less likely, but in transport you can have all sorts of interference effects. Then you indeed look at the sum and the difference. Here it's quite clear that alpha 1 and alpha 2 are quite different from beta 1 and beta 2 because of their amplitudes as well. Okay? And also, actually, I don't have the graph today. I'll show you tomorrow. There is a lovely Yamaji angle right here. So this is when you have the minimum and maximum orbits, and if you rotate the magnetic field, at some point, those minimum and maximum will have the same cross-section, and they will interfere constructively, and gives you a very strong enhancement in amplitude at the Yamaji angle. And that's why we also know that this comes from the same orbits. But what I wanted to emphasize here, actually, was that we have band structure, we have data, and in this particular case, we should be straightforward, reasonably good metal. All the band structure overestimate the real data. So let's, if we look at the real data here, but the calculations gives us bands which are slightly heavier, larger than compared with experiments. And also this particular bands we don't seem to see. So in order to account for this, what we've done, and since then it's been proven to be a general effect, we think that both electron and hole bands need to be smaller than they are in calculations. And often this is called like a red-blue shift effect, meaning that there is some interaction which makes both electron and hole bands smaller. And this is one of the possible explanations presented in this reports in 2009, that if you have strong interaction between electron and hole bands, then that can lead to shrinking of the Fermi surface. Both hole and electron will shrink at the same time. And it's a possible evidence for strong nesting between the electron and hole bands. Obviously, quantum oscillations also can tell us about how strongly electronic correlations are here. And in this particular case, the effective masses are only enhanced by a factor 2, telling us that this is not a strongly correlated system, just slightly mildly correlated. Now, so we established that this compound, it's a good example to show that the band structure features can account for the experiment. So the system, it's in an itinerant model and can be described both by experiments and simple band structure calculation reasonably well, and in the case where the correlations are quite modest. So another interesting thing is that if we just do this isoelectronic substitution, so we have iron phosphorus here, and we replace with arsenite. As I said, usually it doesn't have a doping effect, it's just a chemical pressure effect. The difference between this compound resides in the position of the arsenite above the plane. So here we have a 0.65, whereas for phosphorus case is 0.63. So these tiny differences then cause a major change in the orbital character of this band. So if we look at the gamma point, what we notice that the dxy band is shifted around, whereas the dxz and yz, this is the tetragonal symmetry. And also, it seems like the electron band and the bandwidth to do with this material is much wider, because this system it's a better metal compared with this material. And the ground state, experimental ground state between these compounds is indeed, this is a low TC superconductor, no magnetic state, whereas this material is it has an antiferromagnetic order, a low temperature. So you can notice from here that the details, the tiny details that come from the structure already has a major effect on what happens afterwards. And that's why understanding how this propagates, I think it's very important. And despite, if you look at the Fermi surface from far away, you will look, oh, they are pretty similar. So my assumption will be that nothing changes, but in reality, there are subtle changes to do with the orbital effects and obviously with the bandwidths, which affect correlation afterwards. And this type of position of the pictogen, which is the only parameter really changed there, has an influence on if the system has nodes or is nodeless, and how one can achieve high TC. And this is a theoretical prediction made for this 1111 family of compounds. And if I put together lots of other system of this isoelectronic compounds where I only replace one atom by its sister compounds, no doping effects, and place them on a general phase diagram, then you notice that every time electronic structure on its own is not sufficient. There are other effects which gives us the final ground state. So here also I have iron selenium, which will be inside a nematic state, and its relating compound, IS sulfur, it's a low TC superconductor right here. Similarly, for the lanthanum, one is antiferromagnetic metal, and if you put the phosphorus, it's right here, low TC. Now, when you have a magnetically ordered state, you expect also the Fermi surface to reconstruct due to the new Brillouin zone, and this is what is found in experiments in the barium-122 in the magnetic state. Now you have all this reconstruction due to magnetism. So all these features can be explained in a simple itinerary picture, thinking about Fermi surface and band structure. However, what they need, the final ground state requires more than that. It requires understanding or orbital characters, understanding the correlations, how the bandwidth changes, and we will see later also the role played by the Hund's rule coupling. So now let's move on to what more we know about the system is that they do have a high density of states. And if we look, yes? I'm not sure how to do that, but oh, you mean the doping level or the comparing with the Hall effect?
Well, also with what we would expect based on chemical assignment of, based on doping.
I think one problem we have to compare, I mean, obviously we can measure from ARPES, we can measure the cross-section areas, and that's reasonably well in agreement with what we think it should be.
My question is pertinent to if there are any localized components to the DNA. If there was a mismatch, then it might have some indication.
Yeah, I will show you how exactly the DXY band manifests. Not always are they are at the Fermi level. Sometimes they are buried underneath. And the way they manifest to be correlated is through the band normalization effects, renormalization effects.
But then you might also imagine that the Fermi surface volume doesn't count the total charge.
You're right, a bit like in heavy fermions. So in the example I show you, that was probably a simple example where we don't have small, large Fermi surface effects. Now, there is also another system, potassium ion arsenide, where there is a very heavy mass, and people thought that this will be a bit like a heavy fermion system. However, there, again, quantum oscillations and band structure seems to be a pretty good agreement. So people don't talk about missing pockets.
band structure in which you're allowed to adjust the chemical potential, or band structure where you take ab initio the chemical potential?
So I'll tell you that band structure also has its own faults and how they manifest. I just show you an example when things are simpler, less correlated, then it's a pretty good descriptive tool to understand what we see. As we go further away from that, things become more difficult. And yes, so they do have a very high density of states, and as you can see here, everything is dominated by the d orbital. Often the p orbitals from arsenite also may have a small influence. Now, because of the high density of states, these systems are very close to the Stoner criteria for magnetism. So that makes them prone to suffer magnetic transitions. And this is the itinerant picture to understand the magnetic phase that we see in the phase diagram. And it relies on the nesting effects. So we have electron bands of similar size to the hole bands in the center of the brilliance zone. So if we have a vector which connects the two, then we will expect to have a very strong enhancement in the Linhart function susceptibility for the vector associated with this nesting. And this can lead to a spin density wave where we will have spatially varying spin density for the two type of spin sum bands. And this is believed to be one of the understanding of magnetism in iron-based superconductor based on the itinerant picture where the Fermi surface is relevant to give rise to this magnetic phase. Now, in the same picture, as I mentioned, the fact that we have high density of states and a very large Stoner parameter, the real part of susceptibility will have a peak and it will drive the system in the spin density wave. But if we move away from it, so if we lose the nesting, the perfect nesting effect, so that means if we dope with electronal hole, in this case with electrons, we make the hole band smaller and the electron bands bigger, then the susceptibility will start develop shoulders, and those shoulders are very important channels to allow for scattering between hole and electron and to promote superconductivity. And this is believed to be one way to understand the phase diagram. As long as you are away from perfect nesting, you remove the spin density wave, and eventually the system would like to pair up because this attraction is caused by the spin fluctuation and relies on this large spin susceptibility. This is just a technical slide to tell you that often in theoretical papers, the way the unit cell of the iron-based superconductor is presented is often represented one ion per unit cell because it's easier to disentangle all the orbital degrees of freedom, where in reality, well, experimentalists like me prefer the 2 ion per unit cell because this is more likely what we see in experiments, also with Arpace or quantum oscillations. And the 2 representation is because, well, the 2 ion per unit cell is necessary because there are 2 ions which are non-equivalent and they are connected by this glide mirror symmetry. Now, another important thing is that when the way you move from one to each other, you just fold it and you move fold it along the diagonal, and then this ellipse crosses the other ellipse here, so you have 2 cross ellipses. But in reality, these 2 cross ellipses are separated from each other because of the spin-orbit coupling. And these are experiments which confirm this. These are Arpace experiments focused on an electron band, which are supposed that 2 cross ellipses show that if you look more in detail, you have a separation due to the spin-orbit coupling effects. And this is a parameter which is now essential. It's of the order of 35 millielectron volts in iron-based superconductors.
Question?
Yeah.
In the previous slide, which of these are experimental data and which of these are
So these are experimental data, and I think these are simulations. So yeah, these are Arpes data focused only on the electron pocket, and this is a cut through the dispersion away from the Fermi level to show actually if you would go through the middle of this plot, you will get different intensity where the different bands are, and the fact that you have separation is telling that the spin orbit is active there. I'll show in a minute that, as I said, DFT is just the first approximation which works for weakly correlated system. Later on, people use the MFT and other effects to account for more complex phenomena. So now coming to the pairing interaction, we go back to the itinerant picture of nesting, where we have this antiferromagnetic vector which connects hole and electron bands, and the real part of the susceptibility has a very strong enhancement, this Q vector. Another way of connecting Fermi surfaces is within the same bands, and this is a smaller Q vector. Sometimes could be also due to electron-phonon coupling or other effects, even nematic fluctuations. And this type of scattering will give a small broad feature in the spin susceptibility. So now this is being used as a test to check what will be the pairing mechanism and what will be the response in neutron diffraction. So these are the calculations I showed you earlier. It shows this very strong resonance the Q vector associated with the nesting vector, which promotes this S plus minus pairing as relevant for superconductivity in these materials. And these are neutron diffraction experiments. Again, the imaginary part of susceptibility versus energy, which has the development of extremely large resonance peak inside the superconductor. So this is a 4 Kelvin peak, which supports that the likely mechanism for pairing in iron-based superconductor, at least in this family of iron-based superconductors, is the spin fluctuation, which will lead to this sign change S plus minus pairing. And these are some pictures to remind you what we mean by different gap symmetries. As you heard last week, in a conventional superconductor, you have an isotropy gap around the Fermi surface. In a D-wave superconductor, you have nodes and a D which changes sign in different parts of the Brillouin zone. In another conventional superconductors, but now with 2 bands, like MGB2, you can have, again, S-wave gaps, but different sizes on the different Fermi surface, whereas in iron-based superconductor, one potential candidate for pairing for the gap symmetry is S-wave-like, but with a sign change between the electron and hole-like bands. So again, we have multiple gaps occurring, and this particular scenario relies on having pairing due to spin fluctuations. And yeah, these are just, yes.
Is that theory, or is that, I think D-wave pairing in the group breaks is pretty well established. Would you regard S plus minus as on the same level of establishment?
Well, I try to show you that experiments show this resonance mode at the exact Q vector associated with antiferromagnetic wave vector inside the superconducting state, which will support an S plus minus pairing. So that's my evidence for it.
But if higher TCs occur in materials that don't have that magnetic structure, doesn't that, I mean, you're supporting one case that supports it very nicely. I agree with you, okay? But if I then take another iron-based superconductor with a higher TC, which doesn't have this resonance, shouldn't I then suggest perhaps that this isn't such a good mechanism?
I think this is the starting point where we can find agreement. Anything else, it falls apart, unfortunately. And indeed, you're right. There are cases where we lose this pocket. We don't have it there anymore. And then we are open to new mechanisms. Yes. So especially in iron chalcogenites, the whole band is missing.
But either you take your S plus minus and say, well, I need another mechanism for another iron base and another one, or you abandon it completely. Really, you can't say, well, I'm going to choose and pick. I think for this material, I'll use this theory, and this one, I'll use another one. Why not? Let's all have our own theories.
I think better friend Ruth.
I would like to have a universal theory, and I hope by the end of this, everybody will go home and start taking a piece of paper and start working out that universal one. However, we are not at that stage yet.
That's true. So that's why I'm suggesting you make a much bigger disclaimer when you present S plus minus.
It's coming through. It's coming through.
If I was presented directly beneath E-ray and right next to magnesium and chloride, those are well established. This is not.
Everything else which falls apart, I'll show in a minute. I just want to show things people agree on, and then what really is not fitting in this picture. Yes?
So next one slide, if you compare the imaginary part of the
This?
Yes. If you convert that to the same units, does it then agree well?
Concerning the units, I cannot comment on this, what's accounted for, what not. I'm not sure if this is particular for the same system, because obviously I think this is for lanthanum iron arsenite, and potentially the experiments are on the barium compound. So there are some discrepancy between systems, but what's similar about them is that they have a hole and electron. So there's this picture that you always have the hole and the electron are present.
But is this peak at roughly the same, I don't know, maybe 10 MeV or something like that, of the order of magnitude?
So in terms of absolute units, as I said, I cannot comment because they are also for different families in this case. So yes, I think somebody needs to check this out. I don't know if I couldn't find in literature. I mean, potentially exists calculations done exactly for this material. Okay, so as I mentioned earlier, so here the pairing is not due to electron-phonon coupling anymore, but due to the exchange of paramagnons and where the spins play an important role. And this is the picture that you see often in the, this type of Feynman diagram seen in BCS, where you have the exchange of phonons, but in here you will have the exchange of paramagnons, and the attractive interaction in this case will be related to the spin susceptibility of the system. Now, the spins play a role, but in iron-based superconductors, we also have the orbitals. And now I'm going to also talk a bit about what the orbitals do. And here are, this is again, I think it's a tie binding calculation trying to mimic the band structure calculations. What is telling us is that the orbital character of these bands changes significantly as we go in different places, the high symmetry points. And sorry, this is not very, these are yellow lines, but so these are the two electron bands, beta 1 and beta 2. And if you go around the Fermi surface in this plane, you cross from a dxy character in this places to a dz character, whereas here you have the dx, the green one is the dyz character, and again the whole bands also change. So what's often found in many systems is that these three orbitals are the most important. So you have, if you are in tetragonal phase, they are degenerate, the dxz and yz are there, and then you have the dxy playing a role. And you can see in the partial density of states, in this particular calculation, which again is done for the lanthanum iron arsenite, the dxy has the largest density, and then the others much less. Well, especially the more three-dimensional type of orbitals. But that means when we think about the pairing, we only thought so far about a two-dimensional plane and about the sizes of the Fermi surface. If you want to think more thoroughly, it's worth emphasizing that this orbital character changes. It has a very strong three-dimensional variation. So if you want to pair up, obviously it's important not only to have available states for scattering, but also that the orbital characters will be the same. Otherwise, the probability of scattering will be less. And this is just a picture to emphasize that the orbital character is a strong parameter to consider, but also it has a three-dimensional variation. Okay, so now I'm going to move away from the itinerary picture into the localized picture, and what can we understand from that point of view. So Piers has gone now, but this is one slide to address the concern he had, that the DFT is not perfect. Okay, so the DFT, when you do the calculation, it overestimates the magnetic moment. Even for this lanthanum-ion phosphorus case, which I show you that experiments are in reasonably good agreement with calculations, if you check what is the magnetic moment based on those calculations, it's very large. And this doesn't make sense because this system is a paramagnet. So obviously it has a problem with magnetism. So experimentally, this is a graph for magnetization versus ruthenium concentration in a 1 to 2. The magnetic moment is strongly reduced as you dope, but also it's much smaller than it should be if you consider localized spins. So a reason for this is suggested to be that we might have very strong fluctuations in the system. And strong fluctuation coupled with strong Kohn-Ruch coupling is likely to make some of the spins to look more localized and other more itinerant. And I think this is a graph showing how the magnetic moment for different type of materials between how it varies either from experiments, so the blue diamond is the experiments. Here is almost 0 for this family, whereas in this case, this is again experiment, I think, for the iron tellurium system is very large. So this is a particular case where the moment seems to be very large in experiments as well. But in general, the expected value of the moment is much smaller than it should be, and that's why this particular techniques, the DFT plus the MFT, are suggesting that we need to think about some of the systems away from itinerary picture, and we have to think like a composite of itinerant and localized spins. And this is a histogram of what probability one can find the iron atoms inside this tetrahedron, and often it's found with a spin of equals 2, but also other types of spin states can be found for iron inside of this configuration, and depends on the different distortions. Kohn rules determines which of the spin state will be achieved eventually, and the smaller the spin state, the stronger the fluctuations in the system. Now, within these localized pictures, obviously we move it onto another topic where it's been described today about magnetism and in other talks we had here. Then the physics of magnetic order is described by a Heisenberg model with different exchanges in plane and outer plane, and sometimes also anisotropy is considered. And this localized picture then can account for this antiferromagnetic stripe antiferromagnetic wave vector. So it can explain why this antiferromagnetic can exist, only thinking that the spins will be localized. And this antiferromagnetic wave vector is the same vector like the nesting vector, which made it difficult to kind of separate which picture to consider, the localized or the itinerant. And I think then further experiments and further discovery of new materials, in a way, told us that things are more complicated. And here is, again, a system where we have collinear antiferromagnetism, where this nesting vector is the same like the collinear antiferromagnetic vector. But when we change the magnetic order, like in iron tellurium, when we have double stripe order, then this doesn't agree anymore. So here, the nesting, so the itinerant picture and the localized picture starts diverging. And this is also the system where we have the largest localized moment. It's telling us that we can't treat it as an itinerant system anymore. And since then, it's been found that magnetic ordering can vary quite significantly between different families, and here is just various type of ordering from collinear antiferromagnet to hedgehog-like ordering, where you have in and out spins varying on this ion lattice, and due to the variation of a magnetization between different sites. So magnetism is not universal. When the systems seem to be quite itinerant, it seems to be collinear antiferromagnetic, but it deviates in many other classes of materials. Now, this is a summary of different type of neutron diffraction experiments comparing lanthanum copper oxide, the typical antiferromagnetic insulator with its dispersion, with some of the finding in iron-based superconductor, which suggests that while certain features can be described by the local spins, there is still enough spectral weight, and the positions of some of these dispersions are changing, and one needs to account also for the role of itinerant electrons. I also thought it's worth remind ourselves that this is susceptibility versus temperature, and if we think about the localized spins, you expect the Curie-Weiss behavior and susceptibility to go up as function of temperature. This is the strontium ion arsenite and barium ion arsenite. The susceptibility goes down. This is before it enters this magnetic transition. And this is the susceptibility of chromium. Chromium is a prototype antiferromagnetic metal, and these materials have very similar susceptibility to what we see in this at least this family of iron-based superconductors. So certain things can fit certain materials, but they deviate significantly when the systems become very itinerant. And as another example for how the neutron diffraction looks like the response in a material where there's no long-range magnetism at all. This is the case of iron selenium, which has a nematic transition, but no magnetic transition at all. And the susceptibility, the imaginary susceptibility has a very broad range of excitation. So it's telling us that despite the fact that the system does not order, it has very strong, likely high energy fluctuation in the systems. And to explain this behavior, or a model to explain this behavior, came from in this paper, where various type of antiferromagnetic arrangement were proposed, and it's been suggested that in this particular material is likely that there is a competition between different type of ordering, and that's why the system, it's likely to look like a frustrated system, and it never orders magnetically. But the spin fluctuations are still present. Okay, so now on another topic about how strong the correlations are in these materials. And probably one example of how strong the correlations are is, again, referring to iron selenium. And these are some of our data where we look at the high energy binding energy with ARPAs. What we found that there is a very broad band here, which looks like a lower Hubbard band. And by comparing the experiment with theory, so these are the experimental data and these are theoretical data, we suggested that it's likely that low Haber band is present in iron selenium. And that requires, the presence of this band requires quite sizable electronic correlations, U of about 4 electron volts, and a Hund's rule coupling of about 0. Electron volts to explain the behavior. So some features are there. And then let's look another example where I mentioned earlier the potassium ion arsenide. So this is the whole dope and member of the 1-2 family. The specific heat has extremely large value. This is about 100 millijoule per mole, which suggests that there are very strong correlation, very close to one might find in a heavy fermion system. Another interesting feature is that resistivity, it's very close to reaching the Mottiofer limit at room temperature, and it shows quite bad metallic behavior before becoming more metallic-like. And this has been suggested that it's a signature of incoherent to coherent transition in transport in the same compound. So a more direct way to understand what might happen is from looking at the different orbital characters of the different family of compounds. These are Ironbased data. This is binding energy versus momentum. And these are the different band renormalization factors for different bands with different orbital character. And as we move from the 1-2 family, which is the most itinerant, towards sodium ion arsenide family, towards this iron chalcogenide family, what we notice is that the blue band, which is a XY character, becomes heavier and heavier. So this is telling us that this DXY band becomes more correlated, and this is likely where the localization effects might occur. And it can also affect then how the transport is described. And this is a graph with lots of details about the different band normalization extracted from Ironbased in a review article. So again, the most important features I want to emphasize is that this DXY band renormalization increases significantly with the whole doping, being a factor 7 in the potassium case. So it looks like the whole doping effects drives this, sorry, the DXY band. This is DXZ band. Something is not right. The DXY is supposed to be the most correlated one, and I think I lost one of the graphs here. Okay, let's, these are calculations now to try to understand these effects. These are again using the DFT plus DMFT calculations. So these are the effective mass in relation to the band mass for different compounds. It's telling us that in the chalcogenized family, the band renormalization due to the DXY band are the most enhanced. And often this is referred either like as orbitally selective correlations. Sometimes people refer to Hund's like metal, where some of the bands look more localized than others and have stronger correlations. And the same work tried to explain why this mass enhancement is increased as we hold doped. So this is the mass from experiments, from different type of experiments, and these are their calculations. And they give a pretty good description that indeed the main effects is determined by this localization, by increased mass enhancement of to do with the DXY orbital. And they propose a generic phase diagram one can use when you have very strong correlation, where you look at the orbital from the half filling. So in this case, this is where the spin density wave phase is located, and this is where the So here we have the d5 orbitals, where we have we lost one electron, and this should be a multi-insulator state, but as we dope the system with electrons, eventually will become a superconductor and a Fermi liquid, similar to a picture that you might think might exist in cuprates. I think this way of representation, where you account for correlation, but also for the average doping of each orbital, may be a good way also to understand the system where correlations are important. Okay, so now a bit about the nematic electronic state. So I mentioned earlier that the first transition happening at high temperature, it looks like the system develops strong anisotropy in plane. So it loses its C4 rotational symmetry, and it's called a nematic electronic state. And this terminology has been borrowed from nematic crystals, where you have this unidirectional orientation of these liquids and the loss of the rotational symmetry, despite the fact that you don't change the translational symmetry of the lattice. So when the question is always what determines this, this phase. The way it manifests by extremely large anisotropy between the A and B axis. So already in the tetragonal system. So we know that something is happening to the system before even it enters this transition. But it can also have an origin coming from its susceptibility along this direction. So another thought is that it could be spin-driven Ising nematic order. Now, if it's electronic, one we can think of either orbital degrees of freedom. We have the breaking of the degeneracy, and we have some sort of orbital order effects, or we can have interaction, which can deform the Fermi surface. So all these effects will lead to anisotropy in the electronic behavior. And these are some experiments showing the large difference between the rho A and rho B as function of temperature, which is a factor, I think a factor 6 to 8, than what you expect from a simple lattice distortion. So the lattice feels the transition, but because the effects which causes we think it's electronic, it just responds to this effect. So the changes in electronic behavior are much larger than the ones based only on a simple structural transition, and that's why it's believed to be an electronic-driven transition. A way to test this nematic order is through nematic susceptibility measurements, which I'll describe more in detail tomorrow. But in reality, what you measure here, you look at the degree of anisotropy in transport to a tiny amount of strain. This is equivalent like you will do susceptibility measurement to test if a material is an antiferromagnet or a ferromagnet. You measure its susceptibility in a tiny magnetic field. Here you measure the susceptibility of the system in a small amount of strain, and then this type of susceptibility, nematic susceptibility this time, it has a Q-revised law, and that is used as another signature that this nematic state exists. Now, another proof for the origin of the electronic transition at the TS is the jump in specific heat. And this is the case of iron selenium again. At this temperature, the jump is very small. It's 5.7 millijoule per mole, which is what you expect for electronic contribution to the specific heat. So this is another evidence that it could be electronic transition. Now, as I mentioned, the origin is still under debate, and here I'm just presenting two cases. One to do with orbital ordering effects, and when we think about orbital ordering in a metallic system, we think about the difference in their occupancy for the the two orbitals, which are the general dxz and dxy orbitals. And this difference in orbital occupancy can vary across the unicell, and that can give rise to a type of order parameter. Obviously, a very long time ago, in 1958, presence of nematic state has been postulated to occur in a Fermi liquid in the presence of very strong interactions. So the interactions themselves can lead to a distortion of the Fermi surface and cause this nematic state. I forgot to mention here that the orbital ordering effects obviously eventually will distort the Fermi surface, and it makes it very anisotropic, and this is what we determine in experiments. A simple theoretical model which I particularly like to try to understand where to look for the effects of nematicity has been provided by Rafael Fernandez and Oscar Wafek in this paper, where they only focus on the high symmetry points and what will happen at the band dispersions in those regimes. So, for example, at the gamma point, the splitting of the whole bands in this particular symmetry group should tell us the splitting is given both by the nematic effects and spin-orbit coupling. Whereas at the end point, the splitting of the spans occurring here are a signature both of the nematic effects, so you have the lifting of the degeneracy, but also due to the hopping anisotropy between the dxy orbitals. And if we look at the experiments, and this is the case of the iron selenium sulfur, these are the whole bands. This is above the structural transition, so this is the tetragonal phase. Now this is inside the nematic phase, and indeed we see that the bands look like they repel each other. The inner band, whole band is pushed down, and the outer whole band is pushed up, and this type of enhanced splitting is caused both by orbital ordering effects, by the nematic state, and also by the spin-orbit coupling. And this is the way we can estimate the size of this orbital order of about 30 meelectron volts and of the spin orbit of about 20 meelectron volts. And also, we see the distortion of the Fermi surface from the tetragonal case to a single elongated ellipse as another signature of the nematic phase. There are two ellipses here because the system forms domains as you go through the transition, which complicates life a bit. Now, there are lots of studies under strain, which I'm not going to talk about this time. But when we compare a system in the nematic state and outside, it's obvious that this C4 symmetry is preserved when we are in the tetragonal phase, whereas we break it inside the nematic phase. So concerning the orbital order, there are lots of proposals, and this is still a very active area of discussions, especially in iron selenium. And this is caused by various effects in experiments and the way the distortions happens and the way the Fermi surface are elongated. So a bit like in superconductivity, you can think that you will have an order parameter which changes sign and between different sites. Initially, it was proposed that the fair orbital order, meaning everything distorts in the same direction, is the responsible for the observed effects. But lately, it's been found that what you see at the whole bands and the electron bands is quite different. So there is a very strong momentum dependence of these orbital effects, which requires further understanding of the exact order parameter for this orbital ordering. And why do we care about orbital orders? Eventually, we care because the way we understand and the origin of it is likely to determine what order and what type of superconductivity will be stabilized. So if you only have the spin nematic and you have a positive interband coupling here, then this type of superconductivity will be dominated by magnetic fluctuations, and then S plus minor will be will be the likely candidate. But now if you think from that the orbitals are important and you might have charge density wave or nematic orbital order effects, then you might consider that the charge fluctuations are important. In this case, the interbrain coupling will be negative, and potentially you will look for a different type of S++ superconductivity. Okay, so now a few slides for peers about criticality and strange metal behavior. And this is obviously, like in other strongly correlated systems, criticality can be found if you tune one parameter, especially in this case, if you tune magnetism close to 0, one you expect that one could find a quantum critical point. And it will give unusual metallic behavior and divergence in certain property. And in this case, the arsenate phosphorus substitution is considered as a good way to tune because you don't add doping, so you keep the system quite clean, and you can reduce the bandwidth in this way, so you can reduce correlations. And indeed, experimentally it's been found that in barium ion arsenide phosphorus, you do have this non-Fermi liquid behavior, and the way it manifests, this is resistivity versus temperature. You see that close to 33%, you have very linear resistivity in temperature. And as you go away, the system becomes more Fermi liquid-like behavior. This is found in many other systems, often in vicinity of antiferromagnetic critical point. Linear resistivity and unusual behavior. We also did quantum oscillation experiments, and for the electron bands seen in experiments, the effective mass seems to diverge as approaching this possible quantum critical point. This is again a signature of the quantum behavior, quantum critical behavior, and the mass is strongly enhanced. Now, what is found in antiferromagnetic system seems to be different from what we find if only the nematic order is present. And these are some of our new data about transport in iron selenium sulfur under pressure. So here we don't have any more magnetism, we only have a nematic phase, and we suppress with pressure. And we were looking to see what's the behavior in the vicinity of this nematic endpoint. Does it have critical behavior or not? And these are our resistivity data, again shifted for clarity. All these are the superconductive phases. And in this material, so if we look close just above 5, there is no linear resistivity behavior. Instead, what we found that just around this regime, the resistivity follows a 1.5 power law. So this is quite different to the case where you have antiferromagnetic fluctuation be present compared with only nematic fluctuation. So it's likely to be a different type of behavior. And also, if you look at how the exponent vary with the temperature in this regime, indeed this exponent stays close to 1.5 in the where it should be a critical regime. And these are similar data now using not pressure but chemical pressure. Again, we find 1.5 power laws instead of linear resistivity in the vicinity of the nematic endpoint. And interestingly, the correlations do not diverge when we approach a nematic endpoint. So this is telling us that these critical fluctuations are somehow quenched. And our understanding so far is that there is a coupling with a lattice along certain direction, which is likely to cause this quenching of critical behavior when only nematic phases are present. Okay, so, I'm reaching the end. Probably what else? There's more to come, but I will leave more for tomorrow. About the gap symmetry, maybe to address Pierre's question, indeed the gap symmetry is not universal. And there are lots of proposals for what it could be, including D-wave when you don't have hole bands. And these are what experiments show, that often you have multi-band system with different gaps for different band structure, and also you can have anisotropy. In the case of iron selenium, very anisotropic behavior has been found and has been suggesting again to be due to the fact that there's orbitally selective pairing. Again, not only that the orbital degrees of freedom play a role in the nematic order, but also potentially in pairing in these materials. And sometimes a proposal for D-wave has been suggesting in the potassium ion arsenide, but depending on the system, this is thermal conductivity, can be described either as a clean D-wave or potentially S-wave with lots of accidental nodes. Similarly, penetration depth shows linear dependence, which often suggests the presence of nodes, and other systems show there are no nodes there. So I think the issue with gap symmetry is very dependent on sample qualities. Often the samples which are the cleanest seems to have nodes, whereas the dirtiest one are nodeless. And the night shifts excludes the triplet pairing in iron-based superconductors. So this is at least something which I think people agree that there is no triplet superconductivity. Yes?
You can get considerable night shifts in fully gapped triplet states. And no one knows where zero is in the night shift. So you don't know whether it's 100% night shift or 30% night shift. And so if you had a fully gapped triplet state, it could actually reproduce these night shifts.
You exaggerate.
Potentially, I agree with you. As I said, this is what the experiments show. So tomorrow I'm going to talk about iron-based iron chalcogenides, which is another fascinating family, and I will focus on that tomorrow. So thank you very much.